Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. What if the numbers 1 and 1001 were considered profoundly closer than the numbers 1 and 2? This question, on its face, seems to violate the most elementary intuition we have about the number line, that familiar linear progression stretching from negative to positive infinity. Yet the entire edifice of modern number theory rests upon the startling revelation that our standard conception of distance, measured by absolute value, is merely one perspective among many. If, for instance, our primary concern is divisibility by the prime number 5, then the numbers 2 and 27 are intimately related, their difference being 25, a multiple of 5 squared. In this peculiar landscape, two numbers are close if their difference is divisible by a high power of 5. This is the conceptual space where our story begins, a world re-envisioned by the German mathematician Kurt Hensel at the turn of the 20th century. Hensel's work emerged from a fertile and yet deeply challenging period in the history of mathematics. The late 19th century had witnessed the heroic achievements of the German school of number theory, with figures like Ernst Kummer, Leopold Kronecker, and Richard Dedekind forging powerful tools to explore the arithmetic of algebraic number fields. These are realms extending the familiar rational numbers created by adjoining roots of polynomials, such as the field containing all numbers of the form a plus b times the square root of -5. Within these new worlds, the comfortable laws of arithmetic, like unique prime factorization, often collapsed. The great project of the era was to restore order, to understand the anatomy of these generalized integers. A key insight, developed with breathtaking scope by Dedekind, was the concept of the ideal, a special subset of numbers that stood in for the missing prime factors, thereby recovering a form of unique factorization. This work, while monumental, carried with it a tantalizing and sometimes frustrating parallel. Mathematicians recognized a profound, almost poetic, analogy between the theory of algebraic numbers and the theory of algebraic functions. An algebraic function field can be thought of as the collection of all rational functions, ratios of polynomials, that can be defined on a given algebraic curve, a geometric object like a circle or an ellipse. The prime ideals in a number field behaved in many ways, like the points on an algebraic curve. For instance, studying the factorization of a prime number like 7 in a larger number field felt remarkably similar to studying how a function behaves in the immediate vicinity of a specific point on its curve. This correspondence was explored with particular depth by Dedekind and his collaborator, the algebraist Heinrich Weber. Their 1882 paper, Theory of Algebraic Functions of One Variable, laid out the analogy with stunning clarity. They demonstrated that one could build a theory for algebraic curves using purely algebraic and arithmetic methods, mirroring the techniques developed for number fields. The analogy was a source of immense intellectual power, allowing insights from geometry to illuminate problems in arithmetic and vice versa. It suggested a deep, underlying unity in the mathematical cosmos. However, the connection remained primarily a source of inspiration, a guiding metaphor. The tools of one domain were difficult to transport directly into the other. In the theory of algebraic functions, a mathematician could study the local behavior of a function near a point, say the point x equals c, by expanding the function as a power series in the variable x minus c. This technique, central to complex analysis as perfected by Carl Weierstrass, provided an infinitely precise lens for examining the function's properties in an infinitesimal neighborhood of that point. The The question that haunted the number theorists was whether a similar tool could be forged for their own domain. Could one zoom in on the arithmetic properties of the integers surrounding a single prime number p with the same analytic precision that a power series provided for a function? This was the intellectual inheritance of Kurt Hensel, a student of Kronecker and a deep admirer of Weierstrass. Hensel was uniquely positioned to bridge this conceptual gap. He possessed Kronecker's arithmetical sensibilities alongside a profound appreciation for the power of analytic methods. He looked at the beautiful sweeping analogy of Dedekind and Weber and saw an opportunity for something more concrete. He sought to transform the metaphor into a mechanism to build a true analytic theory for the integers. His stroke of genius was to take the idea of a power series expansion literally, where Weierstrass would expand a function in powers of a variable x. Hensel proposed to expand a number in powers of a prime pa. To understand the problem this immediately solved, we must consider the classical technique of solving polynomial congruences. Suppose one wishes to find an integer x such that x squared is congruent to 2, modulo the prime 7. This is straightforward. X equals 3 works, since 3 squared is 9, which leaves a remainder of 2 when divided by 7. The next step in the classical method is to lift this solution to a higher power of 7, for instance to find a solution modulo 49. One seeks a number of the form 3 plus 7 times k, whose square is congruent to 2 modulo 49. A bit of calculation reveals that k equals 1 is a valid choice, yielding the solution x equals 10. One could then repeat this process, lifting the solution modulo 49 to a solution modulo 343, which is 7 cubed, and so on, ad infinitum. This procedure, while effective, is an infinite staircase of discrete, painstaking steps. One obtains a sequence of solutions 3, 10, and so on, that are progressively better approximations, yet there is no single object that represents the ultimate solution to the equation. X squared equals 2 in the world of 7-based arithmetic. Hensel's revolutionary idea was to create a world where this infinite sequence of approximations converges to a single well-defined entity. He constructed a new type of number, a p-adic number, which could be represented as a formal power series in the prime p. In the 7-adic numbers, for example, there exists an actual number which we can write as a series with coefficients between 0 and 6, say a sub 0 plus a sub 1 times 7 plus a sub 2 times 7 squared, and so on. This series, when squared, would equal 2 exactly. The sequence of solutions modulo 749 and 343 that we found earlier are simply the partial sums of this infinite series. Hensel had invented a complete number system, a continuum, built around the arithmetic of a single prime. He replaced the laborious step-by-step lifting process with the powerful machinery of analysis. A problem that was fundamentally arithmetic was now reframed in a context where concepts like limits, convergence, and infinite series had rigorous meaning. This invention, which he first presented in a paper in 1897, was far more than a clever computational shortcut. It was a foundational act of creation. Hensel had constructed an entirely new metric space for the rational numbers, a new way of measuring distance. In the 5-adic world, the number 25 is smaller than 5, and 125 is smaller still. Sequences could now converge in ways that seemed utterly paradoxical from the traditional viewpoint of the real number line. With this single brilliant stroke, Kurt Hensel provided the concrete, analytical tool that the Dedekind-Weber analogy had lacked. He gave number theorists their own version of the power series, a microscope for peering into the intricate, local structure of the integers, one prime at a time. The beautiful metaphor had become a tangible, calculable reality, opening a universe of mathematical possibilities whose exploration continues to shape the frontiers of the discipline. To give this new mathematical universe rigorous meaning, Hensel had to construct its foundations from the ground up. The central challenge was a profound one. How does one define a notion of size or distance for rational numbers that captures arithmetic information about a specific prime, a notion that could supplant the familiar absolute value? The answer he developed was a three-step masterpiece of logical construction, a process that redefined proximity and built an entire world upon a new axiom of measurement. The first step was to introduce a function that would serve as this new yardstick. This function, the p-adic valuation, assesses a number's relationship to a chosen prime, p, for any integer. Its p-adic valuation, denoted nu sub p, is simply the exponent of the highest power of p that divides it. The valuation of 25 for the prime 5 is 2, since 5 squared is 25. The valuation of 50 for the same prime is also 2, since 50 is 2 times 5 squared. For an integer like 7, which 5 fails to divide, the valuation is 0. Hensel extended this idea to all rational numbers by a simple rule of subtraction. The valuation of a fraction, O over b, is the valuation of its numerator minus the valuation of its denominator. The p-adic valuation of the fraction, 3 over 25, becomes -2. With this, Hensel had a tool that quantified a number's p-adic essence. A high positive valuation signified deep divisibility by p. A large negative valuation indicated a denominator saturated with powers of p. From this valuation, the second step was to define a new absolute value, and with it, a new geometry. The p-adic absolute value of a number x, written as the absolute value of x sub p, is defined as p raised to the power of the negative of its p-adic valuation. This inverse relationship is the core of the entire system. A number highly divisible by p, having a large positive valuation, yields a very small p-adic absolute value. For the prime 5, the absolute value of 25 is 1 over 25, while the absolute value of 125 is 1 over 125. Numbers that appear large on the real number line can become infinitesimally small in the p-adic sense. This new metric gives rise to a geometric space with properties that feel alien to our spatial intuition. It is a non-Archimedean space, a world that violates the axiom stating that for any two lengths, one can add the smaller one to itself enough times to exceed the larger. Here, that principle fails. This failure is captured by a stronger version of the triangle inequality, known as the ultrametric inequality. It states that for any two numbers x and y, the p-adic absolute value of their sum, x plus y, is less than or equal to the maximum of their individual p-adic absolute values. The consequence of this is startling. In any p-adic triangle, the two longest sides must have equal length. Imagine 3 points in this space. The distances between them, say the p-adic absolute values of x, y, and x plus y, must conform to this rule. If the absolute value of x is larger than the absolute value of y, the ultrametric inequality forces the absolute value of their sum to be equal to the absolute value of x. The two larger sides of the triangle are identical. Every triangle is isosceles. This property transforms the geometric landscape from a continuous line into a vast, branching, fractal-like structure. Points are close together if they share a deep, common divisibility by p, forming tight clusters that are themselves separated by vast gulfs from other clusters with different arithmetic properties. The third and final step in Hensel's construction was to address the completeness of this new space. The rational numbers, when measured by the standard absolute value, are famously incomplete. They are riddled with holes, points like the square root of 2 or pi, which are the limits of sequences of rational numbers yet are themselves irrational. The field of real numbers is formally constructed by filling in all these gaps, a process known as metric completion. Hensel recognized that the rational numbers were likewise incomplete with respect to his new p-adic metric. There existed Cauchy sequences, sequences whose terms get progressively closer to one another in the p-adic sense, that converge to limits outside the field of rational numbers. Applying the very same rigorous completion procedure developed by Cantor for the real numbers, Hensel defined the field of p-adic numbers, denoted q sub p, as the metric completion of the rational numbers with respect to the p-adic absolute value. For every prime p, a new, complete field of numbers was born, standing as a sibling to the field of real numbers. What then does a number in this world look like? A p-adic number is represented as a formal power series in the prime p, with a structure that mirrors and inverts our familiar decimal system. A real number has a finite number of digits to the left of the decimal point, and can extend infinitely to the right. A p-adic number, conversely, allows for a finite number of negative powers of p, but extends infinitely to the left. Consider the task of finding the number -1 within the 5-adic system, q sub 5. We seek a number which, when 1 is added, yields 0. The answer materializes as an infinite series of 4s, the number whose base 5 representation is ellipsis 4 4 4 4. Let this number be x, which is the sum of 4 times 5 to the power of 0, plus 4 times 5 to the power of 1, plus 4 times 5 to the power of 2, and so on. This series converges in the 5-adic metric because the terms, having ever higher powers of 5, become progressively smaller. If we add 1 to this number, the first term becomes 1 plus 4, which is 5. This 5 can be carried over, combining with the next term to produce 5 times 5, or 5 squared. This process continues indefinitely, a cascade of carrying over that leaves a trail of zeros. The sum is 0. Algebraically, the series for x plus 1 is exactly 5 times the series for x plus 1. The only finite number satisfying the equation z equals 5z is 0. The arithmetic is perfectly sound. Hensel had created a self-consistent world, complete with its own analysis and its own bizarre, yet beautiful, arithmetic. He had forged a new lens for viewing the integers, providing a family of number fields where the deepest arithmetic truths could be magnified and explored with the full power of analytic machinery. From the elegant architecture of the p-adic numbers, we now turn to their remarkable applications. Hensel's ingenuity extended beyond mere construction. It yielded powerful tools for solving problems previously intractable. Central among these is Hensel's lemma, a result that showcases the surprising effectiveness of his new arithmetic. The problem Hensel addressed was the systematic lifting of solutions of polynomial congruences. Imagine attempting to solve a polynomial equation modulo a prime number. A solution modulo p might exist, yet this doesn't guarantee a solution modulo p squared, p cubed, or any higher power of p. Hensel's lemma provides a precise criterion for extending such a solution to higher powers of p. This criterion is elegantly simple and relies upon the polynomial's derivative. If a solution modulo p exists, and the derivative of the polynomial at that solution is non-zero modulo p, then a unique solution exists, modulo any power of p. The method Hensel devised bears a striking resemblance to Newton's method for finding roots in real analysis. Newton's method iteratively refines an approximation to a root, using the function's derivative. Hensel's lemma provides a p-adic analog, a procedure for iteratively refining an approximate solution modulo p to obtain a precise solution in the p-adic numbers. This provides a powerful tool for analyzing polynomial equations in the p-adic world, a world Hensel himself had brought into existence. The impact of Hensel's lemma reverberates throughout number theory. Its applications are numerous, ranging from the analysis of congruences to the study of more intricate arithmetic structures. Its influence extends far beyond its immediate applications, serving as a foundational element in numerous advanced areas of mathematics. The lemma's elegance and power lie in its ability to transform difficult problems in modular arithmetic into iterative procedures readily amenable to computation. This algorithmic aspect has modern relevance, particularly in computational number theory, where efficient algorithms are paramount. Hensel's lemma provides an elegant and effective solution to a core problem, showcasing the power of his p-adic framework. A further consequence of Hensel's work is the local global principle, also known as the Hasse principle. This principle addresses a profound problem in number theory, determining whether a polynomial equation possesses rational solutions. The problem's difficulty stems from the intricacies of the rational numbers. The local global principle offers a powerful, albeit imperfect, strategy for tackling this challenge. It reformulates the global problem of finding rational solutions into a series of local problems. These local problems are considered over the real numbers and over each p-adic field, one for every prime number p. Hensel's p-adic numbers provide the framework for the local problems over the p-adic fields. If a polynomial equation has a solution in the real numbers and in every p-adic field, then the Hasse principle suggests the existence of a rational solution. This is a remarkably powerful idea. It reduces the complexity of a problem over an infinite field, the rationals to a collection of problems over complete fields, the reals and the p-adics. The local problems are often easier to solve, making the principle a valuable tool for investigating Diophantine equations. The principle's power lies in its ability to decompose a complex global problem into a series of more manageable local components. However, the Hasse principle is not universally applicable. There exist polynomial equations that have solutions in the reals and in every p-adic field, yet lack rational solutions. This highlights the limitations of the principle, yet it remains a crucial tool in the study of Diophantine equations. Its very existence, born from Hensel's innovative work, fundamentally altered the way mathematicians approached these problems. The principle's impact is profound, providing a framework for investigation even when it doesn't guarantee a solution. It transformed the landscape of Diophantine analysis, offering a novel and powerful perspective on a class of problems that had previously seemed intractable. Its enduring influence is evident in the continued research into its exceptions and its applications in various branches of number theory. The local global principle stands as a testament to the far-reaching consequences of Hensel's creation of the p-adic numbers, a creation that continues to shape mathematical research today. The systematic exploration of these local problems made possible by Hensel's work opened new avenues for understanding the intricate structure of rational solutions to polynomial equations. The local global principle, in its elegance and its limitations, represents a pivotal moment in the development of number theory, a moment forever linked to the name of Kurt Hensel. Beyond his groundbreaking theoretical contributions, Hensel's influence extended far beyond the confines of his own research. For decades, he served as the editor of Krell's journal, a position of immense responsibility and influence in the mathematical world. This role shaped the very trajectory of German mathematics for a generation. His discerning eye for significant work,
His meticulous editing and his commitment to fostering a vibrant intellectual community transformed the journal into a leading platform for the dissemination of cutting-edge research. He curated a collection of papers that reflected the best of contemporary mathematical thought, ensuring the journal remained at the forefront of the field. This editorial stewardship, a less visible yet equally profound contribution, cemented his place as a pivotal figure in the development of mathematics. The early 20th century witnessed the rise of a destructive ideology that cast a long shadow over the intellectual landscape of Europe. The escalating power of Nazism presented a profound challenge to academic freedom and the pursuit of knowledge. Hensel, a distinguished mathematician of Jewish descent, found himself caught in the crosshairs of this rising tide of intolerance. In 1935, he was dismissed from his professorship at the University of Marburg, a stark and cruel consequence of the Nazi racial laws. This dismissal marked a devastating turning point in his life, forcing him into a period of enforced isolation from the academic world he had so diligently served. His profound contributions, once celebrated and central to the mathematical discourse, were now rendered largely irrelevant by a regime that valued ideology over intellectual merit. The silence imposed upon him was a profound loss, not only for Hensel himself, but also for the mathematical community. Despite these tragic circumstances, Hensel's legacy continues to resonate powerfully within contemporary mathematics. The p-adic numbers, once a specialized tool within number theory, have since become indispensable across multiple mathematical disciplines. Their application extends to areas far beyond their initial conception, demonstrating the remarkable versatility and enduring power of Hensel's ideas. In number theory, they have proved invaluable, playing a crucial role in Andrew Wiles's celebrated proof of Fermat's last theorem, a testament to the unexpected connections and surprising power of the tools Hensel created. Their influence extends to algebraic geometry, where p-adic methods provide new perspectives on complex problems, offering unique insights into the structure of algebraic varieties. Even in theoretical physics, these numbers are finding increasing applications, suggesting a surprising and far-reaching influence across scientific domains. The initial focused work has blossomed into a rich and multifaceted area of investigation, highlighting the unexpected reach of Hensel's original vision. The story of Kurt Hensel is one of profound irony. A scholar who dedicated his life to building bridges between disparate mathematical concepts, connecting seemingly unrelated ideas into a unified framework, found himself tragically severed from his own world by an ideology that championed division and exclusion. His creation of p-adic numbers, a framework of remarkable unification, stands in stark contrast to the forces that sought to fragment and destroy his own life and career. This contrast underscores the enduring power of abstract thought, a power capable of creating structures of greater permanence and unity than the transient ideologies that sought to suppress them. Hensel's work transcends the limitations of his era. It lives on, a testament to the resilience of intellectual pursuit and the continuing relevance of his fundamental contributions to mathematics. His life, while marked by personal tragedy, serves as a powerful reminder of the enduring power of ideas and the importance of safeguarding the freedom of inquiry. The mathematical world he helped to shape remains a far more unified and vibrant place, a legacy that continues to flourish despite the efforts of those who sought to diminish it. His intellectual contribution stands as a beacon, shining brightly even amidst the darkness of history. The p-adic numbers, his most significant creation, continue to illuminate the path of mathematical discovery, a fitting and powerful tribute to a life dedicated to the pursuit of knowledge, even in the face of adversity.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.